Okay, so we are ready for week 12, homework number 2. And these are work, W-O-R-K, work word problems, which means that we're figuring out how much energy, how many joules it takes to do different things. And this is definitely going to be on the quiz and definitely going to be on the final. And so I have carefully selected problems that cover pretty much everything. And so this first one, for example, has everything possible in it. And so there's going to be a lot of problems that don't have like the extra meter to secure or aren't losing any sand. And so that would make the problem simpler. So this is definitely the most complex so that it kind of covers everything. Okay, so the first thing you need to worry about is the weight of this cable. And so you're trying to figure out how much it weighs per meter, because as you're slowly pulling it up, then you're going to have less meters left. And so that's going to be one of our variables, one of our things that changes. So if we've got 28 kilograms for 14 meters, then if I divide that by the 14, then I know that this cable is 2 kilogram for every meter. And that is one thing that you need to figure out on every one of these cable problems, is how much does that cable weigh, because that's going to be part of it. Okay, and then we are lifting this up 14 meters, and so that's the start of our integral. So we are lifting it from the ground up to the top of the building, which is 14 meters, and we're going to first deal with the length of the cable. And so we know that that cable is 2 kilograms for every meter, and then gravity always affects that. And gravity never changes, so it's going to be 9.8. They're going to remind you of that every single time. And then a lot of times it's just times x, because you're going x meters, so that's your 0 to 14. But on this one, we have an additional meter of cable to secure that bucket. And so on this one, it's going to be x plus 1. But on a lot of them, you won't have an additional. And so on those, you would just put an x right there. And so again, I picked one that kind of has everything. So on a lot of them, you would just do that weight of the cable times gravity times x. But on this one, we have to do x plus 1 because we've got that extra meters. Okay, but that's not all that you're lifting. You're not only lifting cable, you're also lifting that bucket. Okay, and that bucket, again, we start with the weight. So it weighs 42 kilograms, right? But on this one, it's losing. So it's losing, so we're going to subtract 0.7 kilograms for every meter, so 0.7x, because remember that's per meter, that's as you're raising and lowering it per meter. This was like the only one that had that. So on a lot of them, you're just going to have the 42 because you're not losing anything out of your bucket or your suitcase or whatever you're lifting up. Okay, so that's my weight. And then again, always gravity. Okay, and then dx. So this is my cable. And then this is my bucket. That plus 1 is because I have an extra meter. Some of them won't have that. And that minus 0.7 is because I'm losing sand out of my bucket. A lot of them won't have that. Okay, so I picked one that had everything, but a lot of them won't have this much stuff. Okay, so now we're back to what you should know how to do. So I'm going to simplify this a little bit. So I'm going to do 2 times 9.8 times x, and then 2 times 9.8 times 1. Then I'm going to distribute this in, and I'm going to simplify this a little bit. So then I'll get the integral from 0 to 14 of 12.74x plus 431.2 dx. So that's the same thing. I just distributed and combined like terms. Okay, and then we're going to integrate. So that would be 12.74x squared over 2 plus 431.2x, and we're going from 14 to 0. Okay, so the nice thing is when I plug in the zeros, that's just all zeros. So really all I have to do is plug in the 14 there. And when I plug in 14, I get 7,285.32 joules. So So that's how much energy or work it takes to lift that bucket up those 14 meters while it's losing sand as we go. So again, that one had lots of stuff in it so that it kind of shows you everything, but a lot of them will be simpler than that. Okay, then another one is a suitcase, which is really exactly the same thing. It's only easier because this was the cable plus the bucket. All we have to worry about is the suitcase. We don't have a cable. And so that should make this one easier, right? So we've got a suitcase that weighs 6 kilograms. Gravity always affects that. It's always pulling down and making it feel heavier. And I want to lift it 8 meters. And so this one should be almost the same thing, but a lot simpler, right? So we're going to integrate, and then how far are we lifting it? We're going from the ground up to 8 meters. How much does the suitcase weigh? 6. What always affects it? Gravity, right? And then this time I don't need to worry about X because I'm not lifting that cable with it. And so this is just, it's a constant. That suitcase weighs 6. It's always going to weigh 6. I'm not lifting cable as I go. And so that's it. Like this one is very, very simple, right? This is just a constant suitcase that weighs the same all the time. It's not changing. The cable was changing. And then in this bucket, it was losing sand, so it was changing. But this suitcase, it's not changing. It's a constant. So that's it. Okay, so don't put any X's in there. Don't do anything weird. So 6 times 9.8 is 58.8. And then if I integrate, I'd add that X. And I'm going from 8 to 0. So really, this is just 58.8 times 8, which gives me 470.4 joules. See how much easier that one is? Because I don't have a cable that I'm lifting that's getting shorter as I go, and I'm not losing anything out of my suitcase that's making it weigh less. So on this one, this suitcase is just a constant weight. And so that makes that really, really a lot simpler. Okay, so sometimes they're not as hard as what you think, so don't overcomplicate things. Okay, all right, and then we get to the spring problems. So you've got a lot of problems that deal with springs and stretching it out. And if you've ever played with a spring, you know that it takes a lot of strength to stretch it out past what it normally is. And the further you go, the more it kind of hurts and it takes work. So this spring normally, when it's just sitting there, is 1 meter long. It takes 405 joules of energy to stretch it out to 10 meters. And I want to know how much it takes to go from 3 to 8. Okay, so that's the question. All right, so basically we've got to start, every time you have a spring problem, you've got to figure out this constant thing. And the constant comes from the formula force equals the constant times, and then you integrate your length, and so that would be x squared over 2. And so we're going to start by using this information right here to figure out that constant. So we're going to start with that force right there, 405, that energy, right? Equals some constant that we need to know. And then it's basically x squared over 2 because we integrated it. And so x squared is the difference here. So we went from 1 to 10. So that would be 9 squared. And then because of that 2, we're going to divide by 2. So if I multiply that 2 over, that would be 810. And if I square that 9, that would be 81K. And if I divide that 81 over, then I figure out that constant for this particular spring, which every spring will have its own strength to it. And so this spring has a strength of 10, it has a constant of 10. And so that's going to be what we're going to use to integrate. Okay, so then we're going to integrate, but we're not going to go from 8 to 3 because remember that spring is normally 1. So we've got to take that 1 away. And so we're really going from 2 to 7. And then we bring that constant over here of 10. And then x, because it's changing as we're pulling it. And so anytime it's changing, you put an x. And then dx. Okay. Then we're going to integrate that. So that would be 10x squared over 2, which could also be written as 5x squared. And we're going from 7 to 2. So this time we are going to have to subtract because we've actually got a number down here. So we've got to do 5 times 7 squared minus 5 times 2 squared. And when you do that, you should get 225 joules of energy. To go from 2 to 7, which really is 3 to 8, because we're taking into effect that that spring was already a meter long to begin with. Okay, so that's what I would consider kind of a basic spring problem. And that's how you're gonna do most of them that are just asking for work on a spring. But then they throw this lovely loop in there. And these are, I would say, the most difficult just as far as algebra is concerned. And that is they give you answers. They say it takes 2 joules to take this spring from 2 to 4. And it takes 8 joules more than that to go from 4 to 7. So if I want to go from 2 to 7, then it would be 10 joules total. And they want to know that original length of the spring. And it's not going to usually just be 1 or 2 or 3. It's going to be a decimal of some kind. And so you've got to go through so much algebra to figure this out. Okay, so here we go. So first, I'm going to start with this one. So just completely ignore this second one, and we're going to come up to this first one, and we're basically going to use this almost as our formula to start. Okay, so remember that we did x squared over 2 times k. So we're going to basically do that same thing, x squared over 2 times k, and we're going to set this up, okay? So we're going to do k times x squared over 2. So that's that same thing that we used up above anytime we're trying to find that constant. And we're going to go from 4 minus, call it I don't care what you call it. They don't ever use x. But I think you could, but 4 minus whatever that length was, because remember that's what we do, we subtract that length. 8 minus 1 gave us the 7. So you've got to take 4 and subtract whatever that length of the spring was, and then we've got to take 2 and subtract whatever that length of the spring was. And again, I don't really care what variable you use there, whatever makes you happy. Okay, and then that's going to be kx dx, and we already know what that equals. They already gave it to us. That equals 2. So normally you're trying to figure out the joules, but this time they gave us the joules and we're trying to go backwards and figure out that length. Okay, so then we've got to think about how we do this. So when you're integrating, you take that and you plug it in to the x. We're going to take this and we're going to plug it into the x, right? So we're going to have to do k times this squared over 2, and then minus, and then k times this squared over 2, and that's going to equal 2. So again, lots of algebra. So there's that k over 2, and then I've got to do 4 minus I squared, and I'm going to have to FOIL that. Minus k over 2 times 2 minus I squared. I'm going to have to FOIL that, and I already know that that equals 2. Okay, so now I'm going to do a lot of foiling, and just to make it easier, I'm going to multiply by 2 all the way across so that this will be gone and this will be gone and this will be 4. It's just going to make it a little bit easier. So then I'm still going to have this k out here. I'm going to FOIL this. So that's going to be 16 minus 8i plus I squared. And then remember, I'm subtracting here, so I'm going to subtract all of these when I FOIL it. So 2 squared is 4, but I'm subtracting. A negative 2i and a negative 2i is a negative 4i, but that's going to turn into a plus 4i. And then negative I times negative I is positive I squared, but I'm subtracting. So minus I squared, and then remember I'm multiplying by 2, so now it equals 4. Okay, then I'm just going to kind of simplify that a little bit. And so 16 minus 4 is 12. And a negative 8i and a positive 4i is a negative 4i. And that positive I squared and minus I squared cancel. And that just equals 4. And then remember, what I'm trying to do is get that k. I always want to know what k equals. So I'm still basically doing the same thing. I want to know what k equals. but this time it's still going to have a variable in it just because this is a little more complex. But to get that k by itself, I would divide this over. So from this first little piece, I figure out that k equals 4 over 12 minus 4i, okay, by dividing that over there. Okay, so that is part 1 done. So part 1, I'm done with this. Now I'm going to move on to part 2, which means I'm going to use this piece right here, only this time I'm going to use this for my k. And so remember what I did is I put my k value right here and I integrated, right? So I'm going to do basically the same thing. So now I'm going to set up that integral. Only this time I go from 7 minus I to 4 minus I. So 7 minus I to 4 minus I of that k value we just found, which is 4 over 12 minus 4i. And if you want to reduce that, you can. All those would divide by 4, but it doesn't really matter. And then I put an x after that k value. So we're basically doing the same thing we did above. It's just a little more complex. Only this time I already know what that equals. They told me that that equals 8. So normally you'd be finding that, but on this work backwards one, they already gave it to us. Okay, and then remember what we have to do is we have to integrate this. And so that's just gonna make that x squared over 2. So when I integrate this, then I would get that 4 over 12 minus 4i times, and then that x right there would turn into x squared over 2. And I'm integrating that from 7 minus I to 4 minus I. Only this time I already know what it equals. It equals 8. Okay, so now we get to do a bunch of foiling again because we get to plug those in just like we always do when we integrate. So I'm going to keep that 4 over 12 minus 4i. And then I'm going to take that 2 and just pull it out as a 1/2. And then I get to do a lot of foiling. I get to foil that and then minus foiling that. So again, back to foiling. So 7 times 7 is 49. And then that would be a minus 7i and a minus 7i. So that would be a minus 14i, and a negative I times a negative I is a plus I squared. And then you're subtracting what happens when you FOIL this. So 4 times 4 is 16, but I'm subtracting. A negative 4i and a negative 4i is a negative 8i, but I'm subtracting. A negative I times a negative I is a positive I squared, but I'm subtracting, and that equals 8. Okay, and then I can simplify this a little bit, and I can reduce this. So this 2 is going to go into this 4 2 times. And then if I want to, again, I can kind of simplify that a little. I could make that 1 over 6 minus 2i if you want to. And then when I simplify all this, 49 minus 16 is 33. And a negative 14i and a plus 8i is a minus 6i. And then those cancel. And that equals 8. And then what I would probably do now is multiply this over here. So then I would get 33 minus 6i equals 6 times 8 is 48 minus 16i. And I'd probably subtract the 33 over there and add the 16i over here. So I would get 10i equals 15, and then divide by 10, and I would equal 1.5 meters. Because remember, we were trying to find the original length of that spring. So I equals 1.5 meters. And they don't even all come out that nice. Sometimes they'll come out kind of as a crazy decimal, and it'll say round to the nearest 10th or round to the nearest 100th. And so don't be afraid if when you get down here, it starts getting pretty crazy, because they're not even all quite that nice. But those steps that I just showed you will work every single time. You're basically just setting up that K thing and foiling twice. And as long as you can go through the algebra, you'll be able to solve those work problems. So that should cover most of the different types on the assignment, and I sure do hope that helps.